All right, so we solved the problem of an MDP. So what more is there to learn? Well, actually, still quite a bit, because the problem here was that we assumed that we have the entire MDP as given. And that's usually not the case when we're trying to learn, right? Just like we saw the difference between approximation and learning, there's a difference between planning and learning. Here we're trying to choose a value maximizing policy, whether we're planning or learning. But in the case of learning, we have a learner that's plopped down in a new environment, and they have no idea what the rewards are and what the state transition matrix is. So that means our R and RP, these two things are missing. We don't have them, okay? So what we will need to do is try to learn these two pieces of information, right? We don't have a model that tells us these, but we are going to observe through interacting with the environment what they are, okay? So we want to infer both the rewards and the transitions to states as we go along, and hopefully gain reward while we're doing that. Right? So in a standard MDP where we have everything specified, we actually are asking ourselves, what is the next state and what is the reward given the current state and action? Okay? But in the learning situation, we actually don't have all of these pieces of information, and we now have to learn a strategy. So what we taught you in the previous couple of slides was saying that we know R and we know P, both of these two parts of the Markov decision process, and we can sit back in our lazy boy chair or whatever and plan all we want. Okay, we can simulate it, etc. Okay, but when we are faced in an unknown environment and we don't know what the rewards are and we don't know the state transition matrix, we actually have to interact with the environment first. Okay, and then find out, okay, by taking this transition, I end up in this state, I get this reward, and then if I do that action again, do I get the same reward or not? All of these questions are not answered without having a full MDP. Okay, so we're going to learn the R and the P components while we're doing the actual problem itself. So this comes to the next algorithm, or the last one for this session, which is Q-learning. So Q-learning says that actually what we're going to do is learn the quality or advantage function, right? We're not concerned with having this model because we don't have either of these things. We don't know the state transition matrix and we don't know the reward values, but we can learn them. By taking a particular action, I can observe whether I get a reward or not. That's our small r as opposed to our large R. And then when I take a particular state transition, let's say I do action A in state S, I'm going to end up likely in another state. Okay, I don't know what that state is, but I have to do that action in order to find that. And I'm going to abstract that into a function, this small delta S of A, basically saying that if I do the state, I'm in state S and I take action A, I'm going to end up wherever this function specifies. Okay, so you can think of this as giving an output of the next state, S prime. Okay, so what we're going to say is just like what we did with value iteration and policy iteration, is that we don't have a good Q value function yet. Okay, a good Q action value function. We're going to learn it, and we're going to pretend, just like as usual, that we have a good one, and we're going to optimize it. Okay. So in particular, what we're going to end up doing is something similar to this, okay? Where at the beginning, we get a state from the environment, okay? The agent has to decide what to do. Maybe at the beginning, it just picks the first action that comes along that's available in that state, okay? And it sets that as the policy, right? So it says here, in state S1, you do action A, okay? It's going to perform action A, and then the environment is going to react. Okay, the environment is going to tell us, hey, look, you did action A while in state 1. Now you're in state 2. Okay, and you get to observe this particular reward R2. Okay, at the next time step. Okay, because it was associated with action A1. Okay, that's going to be sent back to the agent. And the agent is going to have to do some updating. It now knows that when I did this particular action, okay, of doing this, that I got a particular reward, my R2, and I'm going to update what my Q value is to a new state. Okay, so I may take the original Q value into consideration and permute it by a bit because now I have some additional information about how good that particular action resulted in. Okay, and I'm going to have another policy for what I'm going to do at that state that again would be set either by random or by previous policy decisions that I've made. Okay. Okay, so you can see where this is going. Okay, I'm actually moving through the state space now because my agent is having to observe what happens in the environment. It's picking up data points for how the states are transitioning. Our delta is a proxy for our full model of P, right? Our script P that we had in the MDP, okay? And our small r's are being observed, like what is the reward for taking a particular action in a state. Okay, so that's the whole idea of Q learning. It didn't seem like that was such a bad thing, right? We got rid of the transition matrix P and the reward matrix R, okay? And we said we're going to learn them, all right? So we're going to learn them by the same procedure. We're going to start with a policy that might be all uniform, okay? But the Q values are going to initialize to 0, okay? So this is going to take up more space because unlike the state value function, the Q value or action value function is specified not only by the state, but also by the action, okay? So we have this cardinality problem S and A, and we're going to select an action. We're going to actually do that action and let the environment tell us what happened with that. It's going to tell us what new state I'm in, what reward did I get for doing that, okay? And then I'm going to update my Q values, okay? This is the information that I have within the agent that's being accumulated over experience, okay? So I'm learning the discounted rewards over time for being in a particular state and taking a certain action, okay? Now, a key observation that we need to make here is that when we set the rewards to always have some positive value, okay, or equal to 0, no negative rewards here, then our Q function is always monotonically increasing in value, right? So this is a good thing because we are always converging towards having the maximum ceiling. When we get to the ceiling and our Q function doesn't change at all, then we know we've met the optimal value for Q, okay? And then if we have our optimal Q, just like we did with value iteration, we can use that Q value to engineer what the policy is, what the right policy is for the situation, okay? So there are still 2 points that we haven't really quite figured out in this algorithm that we sort of glossed over in the pseudocode. The first one concerns this last step, okay? Our last step is the update. It's telling us for our Q values that we approximate, that's why there's a hat here, right? What are the ways that we can update it? Well, in this particular equation here, it says I'm going to set the Q value to the reward that comes at the next state plus the maximum estimated Q for all the subsequent states, right? The subsequent state that I took the transition to, okay? So it's got 2 parts. This is the Bellman part where it's the recursive, okay? So I go back into my table of approximated Q values and I take the one for S prime, okay, and I choose the action there that's maximizing. I put it through a discount. I add it to the current rewards, and that is my estimated Q for this current state. All right. Now, the problem here is that we know when we look at R, we don't always get the same reward, even if we're in the same state and we took the same action, okay? So for example, you might get up this morning, have the same breakfast, but the outcomes could be different because of some externalities, all right? So it's stochastic, so it's not always to say that the real world always behaves in such a way, okay? So we're going to say that R is a stochastic variable and that our transition matrix, our delta, that we're trying to understand as a version of P, okay, is also stochastic, right? We might try to go left in a vacuum cleaner world, and sometimes we're able to go left to a new state. Sometimes we end up in the same state because we're already at a wall, okay? So we need to be able to factor in those types of information into the problem as well, okay? So what we're going to do is, instead of replacing Q entirely, okay, by our new estimate, okay, what we're going to do is decay it in a gradual manner, all right? So we're going to have this alpha value here in blue, okay, which is basically a trade-off function, okay, some type of parameter that's going to tell how much do I trust the original Q values that I had coming in, and how much do I trust the updated Q values that I'm estimating now, okay? So this is the new estimate over here, okay, and this is the historical one, right? This is what we had before, okay? So if we don't want to abruptly change everything, then we are going to set alpha to a non-zero value so that the more times we observe this particular Q, the more we trust our historical settings, right? How many times we've seen this Q value is going to make that Q value more stable over time. Okay. Now there are lots of other ways that we can handle this, but this is the basic idea, is that we don't want to update and abruptly change the Q values, but smear it over time, smooth it like we did with naive Bayes in Laplacian smoothing. The other problem that we had was in the second part of this line, right? In the first line in the loop, which is to select an action, okay? What action should we take? Up to now, we've always been taking the most greedy action that we know is going to maximize our utility, okay? But because things are stochastic, we might get some rewards that are not so good one time, but actually when we buy a ticket or a lottery ticket, sometimes maybe we get a big payoff. Maybe by studying for that test, we finally pass it, okay? So for these reasons, even though we've already gotten estimates of how good a particular action is, we may still want to go back and revisit, okay? So even if we do it in a greedy manner, that may end up being suboptimal because our reward and our transition matrix is not deterministic, okay? So what we are going to do is introduce this idea of an epsilon greedy algorithm, what we call this, okay? That means in most cases, we're going to exploit, all right? We're going to pick action A greedily, okay? When we roll a die and say with 70% likelihood, say 0.7, we're going to do what we think is best, okay? And the other 30% of the time, we're going to say, let's relax a little bit. Let's explore the possibilities of going somewhere else for a change or taking a different action. And this is the idea of exploration, right? So we're going to balance this trade-off using an epsilon greedy algorithm, okay, where epsilon could be set to 0.1 or 0.05 to say how many times I'm going to do this at random part, okay? So there are other ways that we can do that, and you can pause the video or think afterwards what might be a better way of suggesting an action A, okay? And you can think about what we told you on the last slide as well.